Hello, so in this final part of this first chapter in mechanics, the last main idea we're going to look at is vectors and some situations where we use vectors. In particular, vectors to do with something called displacement, velocity and acceleration, right? Which we'll be using all throughout the course. So, first of all, you do look at vectors in pure maths as well. And a lot of ideas from pure maths, the vectors, we'll be using here. So stuff about magnitude, direction, and I and J notation and stuff like that. So you would be in a good spot if you have looked at vectors in pure maths first. However, obviously this is the start of mechanics, the first chapter. I guess some people might do this at the start of the course. So I'll try and do a very quick rundown of all the vector stuff you need to know for this particular bit here. But if you've already looked at vectors, there should be a recap as well. So firstly, think back to GCSE. Maybe you'd be familiar with column notation. So let's say we have 2, 5. Right, now as a vector, if we were to plot this on a sort of XY grid, XY, you'd be familiar with 2 and 5. Well, 2 is sort of the X part, so that'd be 2 on the X axis, then 5 will be the Y part, so 5 on the Y axis there. And so that's our point. Okay, now if we join this from the sort of the origin, right, here we can see that's 2 across, and then 5 up. Okay, so that's the vector, right? You'll be familiar with columns in GCSE. Now, the more formal way we write vectors in A level is not with columns. You can do, that's fine, but a more, I guess, proper way is we use something called I and J notation. Okay, so alternatively, I could say that this is 2 lots of I and 5 lots of J. Okay, these two are the same thing. Now, I and J, if I literally swap X and Y with I, now I underline it because I is technically a vector. Remember, any vector, we underline it. And J for Y. Okay, and so essentially, I and J are just the X and the Y parts. Okay, so another way of writing this vector, 2, 5 as a column, literally 2 across, that's 2i, then 5 up, that's 5j. Okay, so that's 2i add 5j. Okay, there. Another example, very quickly, if let's say we write down the vector minus 4i minus 3j, if we were to plot this vector, again minus 4i, so it'd be minus 4. And again, I is X basically, so minus 4 on the X axis would be there, minus 4, then minus 3 will be down here. Okay, and so there's our point. Okay, so then the vector from the origin is minus 4i minus 3j there. Okay, and then you can write that as a column, so then that'd be minus 4, then minus 3. Okay, so this I and J notation we will be using. Okay, so I is basically the X part and J is the Y part essentially. Okay, the other thing we need to look at is the length of a vector. All right, so let's take this vector again. Right, so again what we've got essentially is we go 4 across, right, 4 across, then 3 down. Right, so we've got this triangle here, so we've got this vector. So if I look at this, if I zoom in on this vector here, again this point, we have the origin, so again this vector is minus 4 minus 3, so we go 4 across then 3 down. Now the length of the vector, so the physical length of the line, right, the length of the vector, right, from the origin to the point here, the length is the hypotenuse of this right angle triangle. This is Pythagoras, right? So if I want to find the length of the vector minus 4i minus 3j, that would be the root of the two sides. So 4 and 3 all squared. So 4 squared and 3 squared, which is just 5, okay? So the length of the vector then, minus 4i minus 3j, is 5, right? Now, we also, the more formal way of writing what we mean by length of a vector is the magnitude, okay? So we don't use length. Again, you can do, but the proper term is magnitude, okay? So the magnitude of a vector is its length, okay? Okay, let me try one more example. So let's say we have this vector here. Let's say I have the vector 12i minus 5j. Okay, let's have a go at plotting this. So 12i, that's 12 along the x, so it'd be positive 12, let's say here. And then minus 5 will be, well, minus 5 on sort of the y-axis. So then my point is here. So my vector is here. Right? So the length of the vector then, well, the length or the magnitude, technically, that's going to be, well, just the two sides all squared. So the two parts, the 12 squared and minus 5 all squared, right? So the two components, the I and the j part, or the x and the y part, all squared, gets you the length of the magnitude. That's 13, okay? So the length of this vector is 13, okay? And that's all you need to know for this part. But again, we do cover that in pure maths as well. But yeah, so you need to be able to plot points. So you need to know what I and j means, how to represent them on the coordinate grid like this, and to find the length of it by doing the square root of the two parts all squared, okay? Like with Pythagoras theorem, okay? So what we're going to do, okay, so with this in mind, we're going to look at displacement and velocity and acceleration now. So let's first talk about displacement or distance. So consider this scenario. Consider we have a point A here, let's say, and then a point B here, right? And then imagine a person, right, starts at A and then they walk, you know, if we connect the path from A to B, right, A to B there, then they walk along this line, right, and then we end up at point B, right? And so the distance then would be the total length they travelled, right? Let's say that is, if we get rid of the people now, let's say that this person walked 10 metres, right? Distance is, say, 10 metres. Now, now let's consider the scenario where we have now a point C down here, right? And this is also going to be 10 metres, right? Actually, let me readjust this. So let's say we have the point A here again now, and then we have a point C down here. And so here again, there's a person at point A, and there's a person, and then they walk to point C, right? So they walked from A to C. Let's say again, the length between A and C is 10, right? So then the distance would then be 10 as well here. Okay, so you can see then in either scenario, if in this first scenario, right, from A to B, the distance is 10 between those two points, and it's also the same distance of 10 from A to C. But so we go from A to B and A to C that way, but the scenarios are different, right? If we just physically just looked at the number for the distance, it's 10 meters either way. But as you can see, the two journeys are different. One's going upwards and one's going downwards, right? So there's a bit of a problem because the distance isn't telling us the length, the sort of the direction, right? It's only telling us the physical length. So not exactly what the journey looks like in terms of their direction, where they're going, right? Okay. This is where displacement comes in, right? Now, let me then consider now, horizontally, right, from A to B. Let's say this distance is 8 metres, and then they went up by 6. So so then we can split up this overall length horizontally and vertically, right? So they walked 8 meters and 6 meters, right? And overall, if you did do Pythagoras, you would get 10. Okay, so this is fine. But okay, so then if we split it up horizontally, so they walked forward by 8 meters and then upwards by 6, right? Now we're starting to get somewhere, because now we're starting to include this sort of notion of direction, so forwards and upwards, right? But actually then, if we use I and J notation, so remember I and J are just sort of, the I is basically the X direction or the X axis, and the J is basically like the Y axis, right? So if we then use I and J, eight, 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 8 steps or 8 units forward is going to be 8i, and then at 6 upwards would be positive 6j, right? So therefore then I can actually then give this sort of line from A to B, the direction from A to B, by this vector here, 8i add 6j. And now that's going to incorporate my sort of direction, right? And so then this vector is what we call the displacement, right? And so the displacement tells me from 2 points A to B exactly what direction I need to go. So firstly, I need to go 8i, so 8 across, and then 6j, meaning 6 upwards, okay? And I get to the same point, okay? So that's, therefore then we can decompose it into I and J, so X and Y, and then we can get the vector, okay? And actually then, if we did the same for this journey here from A to C, let's say again that's 6 downwards, so that'd be minus 6J now, because negative, because it's going downwards. And then going to the left, by minus 8i, okay? So because again I and J, if it's negative, that's because it's going in the negative direction, so left, okay, like the x-axis, right? And so then the vector in this case is going to be minus 8i minus 6j, right? And therefore this is my displacement in this case. So the displacement is the vector for the journey, okay? So hopefully now we've got a much better picture using the vectors for what the journey is like, in terms of, well, how far forwards or backwards you're going, and then how far up and or down you're going. It incorporates the direction as well. And so then you notice, hopefully you notice then, that whilst the distance is the same in both journeys, the displacement vector is different, okay? Because in this case the negatives indicate they're going in opposite directions, so that's the whole idea of a displacement, right? It's the vector, it's a vector that tells me the direction to go from one point to another, okay? So lastly, to reiterate, 8i and 6j would be 8 across, as you can see here, and then 6 up, and then we end up at the point B, okay? Okay. Right. So if I was to summarize this then, displacement is the vector for the how should I word it? Displacement is the vector for the, I guess, route between 2 points. So what I mean by route is from point A to point B. The route is how do I get from point A to point B, okay? So in other words, it tells us how to get from point A to point B. Right. Now, I did kind of hint at this earlier, that I said that the what's it called? The Pythagoras. So in other words, if you did the hypotenuse, right, of this right angle triangle, if you did 8 squared and 6 squared, you would get back 10, which is coincidentally the distance. Well, actually, then, if we then confirm this, if I did then the magnitude of my vector 8i and 6j, so the magnitude of my displacement, if I did that, then that'd be root 8 squared of 6 squared, and then I will get 10. Okay, but coincidentally, 10 is my distance. And so actually then, another cool feature for displacement is actually, if we then do the magnitude of my displacement vector, it tells me the distance, okay? And so therefore distance, I would say, is the magnitude of displacement. Okay, and that distance, you know, tells you what you expect. It just tells you the physical distance or the length from one point to another. Okay, but displacement tells me the vector for the direction or how to get from point A to point B. Okay, right. Okay, so that's distance and displacement. Now we're going to look at speed and velocity, and it's pretty much the same sort of story. Okay. Right, so let's say, let me then copy down my A to B, right? Now let's say then A is the point 2, 1, and B is the point 10, 7, right? And obviously then the length would be 10 still. If you did the distance between 2, 1 and 10, 7, it will still be 10, okay? And again, the change in x, right? The change in x then between 2 and 10, that would be 8. And the change in y from 1 to 7 would be 6. So it's the same journey, right? It's still 8 across and 6 up, right? But now I want to talk about velocity, right? Well, actually, before we talk about velocity, let's look at speed, right? So speed. Let's say the speed of someone walking. Let's say, for example, speed is. Actually, I'm going to do it down here. Let's say, okay, that speed is of someone is 5 meters per second, right? What that means is then speed tells us, and you can kind of look at the units to help you here. Speed is kind of a rate. It tells me how much they're moving per second, how far they're traveling per second, or per minute or per hour, depends what the unit for time is. In this case, keep it simple, meters per second. So every second, that's telling me they're walking 5 meters. So let's say there's someone here starting here, and then after 1 second, the speed of 5 meters per second tells me they move 5 meters. Okay. Then another second later, then 2 seconds, they move another 5 meters. Then if they keep this up, okay. And so overall, then every second they move 5 meters. So overall, then say for the whole 1 second there. Overall, then for 2 seconds, they would have moved 10, right? 10 meters, right? So then what we can say then is this then coincides with the speed distance time formula, which you should be very familiar with from GCSE, and that is distance is speed times time. Okay. And again, we will be using that in this section. It might be a sort of basic formula, but you still need to remember it. Okay. Right, so hopefully you get the idea of what speed is, right? The speed tells me how much I'm moving every second or every unit time, okay? Right, velocity is basically the same, but it's in the vector form instead. So let's revisit this example here, okay? Where I'm moving from point A to point B, there. Now, let me then say it's moving with velocity. So, for example, the velocity of this journey from point A to point B is the vector 1.5 or 2i add 1.5j. meters per second. Okay. Let's say my velocity is this. It's this vector here. So again, velocity is going to be the vector for speed, which we'll see in a second. But the velocity, let's say the velocity is 2i and 1.5j. But what does this mean, right? In terms of this journey, if I'm moving from point A to point B, from point 21 to point 10.7, and I'm moving 8 across and 6 up overall, what exactly does this velocity mean? What that means is, and again, it's analogous or very similar to this speed example, right? With velocity, it's the same thing. It's telling me if I'm starting at point A, it's telling me I need to move by this amount, by this vector every second. So I'm going to add this vector on to the point every second. So let's demonstrate what's going to happen. So I have the point A here. And that is the as a vector then 2 1. Actually no, let's keep it the point 2 1, right? The point A is 2 1. Now the velocity is telling me I need to move by this amount every second. Okay, so if I'm starting at 2 1, I'm adding 2i and 1.5j. So again, the I is basically the x, and the 1.5 is basically the 1.5j is basically the y, which means, say after 1 second, I'm at the point A1, right? So then, actually no, I'll do it down here. A21. Okay, we start at A at 2 1. Now, after 1 second, we're now at the point A1. Okay. Which means we need to add this amount on 2i 1.5j. So we're going to add 2 to my x point, right? Because 2i is basically 2 lots of x. So 2 is originally the x value. So I'm going to add another 2, and now I'll be 4 for x. And originally y is 1 at A. So now I'm going to move by 1.5. So now it'll be 2.5. Okay. And so after 1 second, I'm now at this point A1, this coordinate here. So that is the whole idea with velocity. I'm moving my point, right, by this amount, right, by this velocity. The velocity tells me how much I need to move my point by every second. Okay. If I was to continue this on then, let's say now I'm at the point A2, right? And then I'm going to do the same. So from this point at A1, I need to add another 2i and 1.5j. So 4 add 2 to my x will be 6. And 2.5 add 1.5 would be 4. Okay. I'm going to do the same again then. So now I'm at the point A3 after 3 seconds then. So again, I'm moving every second. I'm increasing by my vector, okay? So at the third point, after 3 seconds then, again I need to add 2i, so 2 add 6 would be 8. Then 1.5j will be 4 add 1.5, which would be 5.5, okay? So now I'm at this point. Now, after 4 seconds then, so now I'm at A4, if I add another 2 on, so 2 add 8 would then be 10, and 1.5 for y, add by 5.5 will be 7. Okay. Well, okay, so what do you notice about this point now? 10.7. I'm now at the point B. I'm now at my destination. Okay. This is now also point B at 10.7. So now I've done my journey. Okay. So that is the whole idea with velocity then. The velocity tells me how much I need to move per second. Okay. So hopefully you can see that, right? And eventually it gets to my destination after so many seconds, okay, if I keep adding by that amount. Right, so again, the crucial difference then between velocity and displacement is displacement gives me the overall vector from A to B, right? If I look at this again then, so my displacement from A to B here is just 8i and 6j. That's the overall journey, right, from A to B. But my velocity, because it's per second, it tells me how much I need to move every second or for every unit time. Okay, so that's the difference, but that is velocity. Okay, and so therefore velocity is a vector again. So velocity is a vector which says how much I need to move by every time t, okay? It could be seconds. If it's meters per second, it could be per minute, it could be per hour, it could be whatever unit we want, okay? But for every unit, every time t in general, okay? And again then, the speed then, is going to again be the magnitude of this, okay? So if I was to work out with this velocity then, this velocity vector, the speed then is going to be the magnitude, right? So it's going to be the magnitude of 2i add 1.5j. If I do that then, that'd be root 2 squared add 1.5 squared. If I do that in my calculator, I get 2.5, and then that would be meters per second, okay? And therefore, because that was 4 seconds, right? If we were then to do my speed times time, so 2.5 times 4 seconds, that indeed gets me 10 meters, which again, as we saw, 10 meters was the overall distance, okay? So we do get distance if we do speed times time here. So there we are. So again then, I will also add again that the speed is the magnitude of velocity. And from now on, this is kind of how I want to think about velocity, speed, distance and displacement, okay? And so there we are. So in summary then, the displacement is the vector that tells me how to get from point A to point B. The distance is the magnitude of displacement, which is the overall distance, or the length of the journey. Velocity tells me how much I need to move by every second, for example. And then speed is the magnitude of velocity, okay? Okay, so we've looked at displacement, velocity, and then distance and speed as well. The last thing we need to look at is acceleration, okay? Now what acceleration basically tells us, basically if the speed of something is increasing or decreasing, okay? Tells us how much the speed of something is increasing or decreasing by. Okay, and in what direction. Okay, so what does all this mean? So, for example, picture I don't know, some sort of car, right? I'm going to do a really bad drawing of a car. There we are. There we are, a car. So let's say they are moving at, let's say, 30 miles per hour. That's my speed, right? Okay. Right. Let's say they're moving to 45 miles per hour, okay? And this is over 1 hour, right? This is over 1 hour, right? So in 1 hour, the car has changed speed from 30 to 45 miles per hour. So the acceleration of the car then, if it's to do with change in speed, or so how much it's increasing or decreasing by the speed, that means in 1 hour it's changed 15. So the acceleration is here 15 miles per hour per hour. Okay. So what that's saying is the speed changes 15 miles per hour, and that's every hour, because every hour we're increasing by 15, right? That makes sense, because in this 1 hour we've gone from 30 to 45, so the change in the speed in the hour is 15, okay? So 15 miles per hour, which is my speed per hour, okay? Okay. Now let's consider this. Let's consider now the car is traveling at 60 miles per hour. And in 1 hour, I'm not gonna tell you what the speed will be, but I'm actually gonna say instead the acceleration in this case is now negative 10 miles per hour, okay? Now that's quite interesting. The acceleration now is negative, right? So that's saying that if it's negative 10 miles per hour, that's saying the speed is going down by minus 10 every hour, okay? So if it's at 60, then after 1 hour it will go down to 50, okay? And that's when the acceleration is negative, okay? Please don't be confused. If it's a negative acceleration, that doesn't mean it's not moving or anything like that, or if it's got negative speed or anything like that. It's still moving, okay? If the acceleration is negative, it's still moving, but obviously the speed is going down, okay? And so in essence, what I've got here, when the acceleration was positive 15, it's speeding up, right? The car is speeding up because it's going from 30 miles per hour to 45, okay? And every hour, if the acceleration is always, let's say 15 miles per hour every hour, then in 1 hour it will go to 30 to 45. Then in the next hour it will go from 45 to 60. Then it will go from 60 to 75, and then 75 to 90, and so on and so on. Okay, the speed will keep going up in that same amount. Right, so when the acceleration is positive, that's saying that the speed is going up. Okay, the car is speeding up. Conversely, when the acceleration is negative, the car is slowing down because the speed will be going down. Okay, so if we were to summarize this, when we have positive acceleration, that means the object is speeding up, okay, or moving faster, or going faster, okay. Conversely, negative acceleration instead means the object is slowing down. Right? And actually this is called deceleration as well. So if something is what we call decelerating, so when we have negative acceleration, when something is slowing down, that's deceleration. Okay? And again, because we're going to have positive and negatives, we take into account again if it's slowing down or speeding up in a particular direction. Acceleration, like with displacement and velocity, acceleration is a vector. Okay? And there we are. So that's the idea of acceleration. It tells me how much the speed of something is going up or going down by. So it essentially tells me if something is speeding up or slowing down. Okay. Okay, so we've got this question first, and we're told to fully describe the motion of the following particles. So what's going on here? Firstly, the positive direction here is to the right or forwards. And so we've got these 4 particles here in different situations. So firstly, we've got particle A. Now, we're told the sign of the velocity and acceleration. They're both positive here. Now, the velocity, if remember, basically is how fast it's moving in the direction. Okay? And the acceleration is dealing with how the speed is changing, so the change in speed. Okay, so is it moving faster or is it slowing down? Okay, is it picking up the pace and becoming even faster, or is the particle slowing down? Okay, so that's the idea of acceleration. So okay, particle A, firstly they're both positive, which means they're both acting in the positive direction, so forwards or to the right. Okay, so forwards, right? So particle A, if they're both positive, then that means the velocity, which basically again is to do with the movement, so how fast it's moving, so it's to do with the movement of it, it's moving to the right, because if the velocity is positive, it's in the positive direction, it's moving to the right. So because the velocity is positive, it means particle A is moving to the right, or moving forward. Okay, moving forwards. Now, we don't know how fast it is because we're not giving us any numbers, okay? We only told the sign. That's so the sign just tells us where, in what direction it's moving to, okay? So it's moving forwards because, again, forwards is the positive direction. Now, the acceleration is also positive. What does that mean? So that means if it's positive, the change in speed is positive, so it's picking up speed, so it's becoming faster. Okay, so it means particle A is fast, is moving faster. So it's picking up the pace as well. Okay, so it's moving faster every hour or something like that, right? So it might move from like 30 miles per hour to 40 miles per hour or something like that, right? If you use the car example. Okay, particle B. Now, particle B, in this situation, we're told the velocity is positive, but the acceleration is negative. Okay, so the velocity is positive. That again means it's moving forward. So velocity is positive, so it means particle B is moving forwards again. Now, the acceleration is negative, so that means it's slowing down. Okay. There we are, it's slowing down, okay? So it's still moving forwards, it's still moving out of speed, but it's starting to slow down, okay? So there we are. Okay, particle C now, we are told, in this example, that both the velocity and the acceleration are negative. So, because firstly the velocity is negative, that tells me to do the physical motion, so is it moving forwards or backwards? Well, if it's negative, it can't be moving in the positive direction, it's moving in the opposite direction, so it's going to move backwards, okay? So, velocity is negative, and that means particle C is moving backwards. Now, this one's quite interesting. The acceleration is negative as well. What does that actually? What that does not mean in this instance, it doesn't mean it's slowing down in the backwards direction, as we just discussed. Because the velocity is negative, it's moving in the opposite direction. But because the acceleration is negative, it doesn't mean it's slowing down in the negative direction. It means it's slowing down in the positive direction. Okay, so that means if it's slowing down in one direction, it's becoming faster in the other. Okay, so it's slower, it's moving slower forwards, which means it's moving faster backwards. Okay, so the acceleration is negative, and that means particle C is moving faster backwards. Okay, and there we are. Okay, now we have particle D, and the velocity is negative and the acceleration is positive. So, firstly, again, the velocity is negative here, which means again it's going in the opposite direction, so backwards. Okay, so velocity negative, which means particle D is moving backwards. And then the acceleration is positive, sorry, wasn't it? Okay, so the acceleration is positive here. So again, that means if it's positive, because the forwards is positive direction, it's becoming faster. It's becoming faster forwards. Okay, it's moving forwards faster, which means it's moving backwards slower. Okay, so that means the particle is moving slower backwards. And there we are. Okay, so hopefully that example just illustrates the idea of velocity and acceleration there. Okay, but there we are. Okay, so we've got this question now, and it's to do with physical vectors. So we're told the velocity of the particle is v is 3I add 5j. So for part A, it says to find the speed of the particle. So again, if we were to just do a rough sort of drawing of what the vector looks like, if we then start here, then 3I is 3 across, and positive, so 3 across, and then positive 5j is 5 up. Okay, so remember, I and j are sort of x and y, or and I is how far across we go, and j is how far up we go, right? Now, overall, this line here, from start to finish here, is the vector. So this is v, okay? That's the vector drawn, okay? So we can draw a vector by splitting it to the I part and then the j part, okay? Now, we want the speed of the particle, but we got the velocity. What you should know is that the speed is the magnitude of the velocity, which we went over. So the speed is going to be the magnitude of the velocity, and again we can represent the magnitude or the length of the vector by these vertical bars. Okay, so the magnitude again is going to be the sort of the Pythagoras, or the root of the two parts, all squared. So root 3 squared and 5 squared, and so that would be root 34. Okay, and so the speed, the units are again meters per second, and there we are. So it's, again, as a recap, the speed is just the length, the magnitude of the velocity vector. Okay. Then part B says find the angle of direction of motion the particle makes with the unit vector I. Right, so again, we did look at examples like this in pure maths. If you haven't already, seen an example like this, again, I is basically sort of the x-axis. So if we plot this on a sort of coordinate grid, 3I and 5j. So 3I, let's say 3 here, and then 5 up here. 3I and 5j. So again, x and y is sort of I and j. Okay. Now, there we are. That's the vector that joins from the origin to the point. Now, the angle the vector makes with I is basically talking about the angle it makes with sort of the y-axis or the x-axis, which is this angle here, from the x-axis to the vector line. I'll call this theta. So we need to find theta. Now at that point, what we can do is actually, this will be the same angle theta in here, right? So we can construct a right angle triangle, right? So this will be 3 across and 5 up, okay? So hopefully you can see now, here and here, these triangles, the same triangle, right? We can find the theta by using SOHCAHTOA, right? So we know that theta is opposite 5, so this is going to be the opposite. The 3 is going to be the adjacent, and obviously the hypotenuse. So we can use tan. So we can use tan theta, which is the opposite over adjacent. And so tan theta in this case, the opposite is 5, and the adjacent is 3. So tan theta is 5/3. So therefore, if we do inverse tan, we get theta to be 59.03 degrees, 0.04 degrees to 2 decimal places. So there we are. Cool. Okay, so here we've got this question, and we're told a man walks from A to B and then B to C. So again, along this line here from A to B, and then B to C here along that line. Okay, we're told that the displacement from A to B is 6I and 4j. So again, remember, displacement just tells me the vector to go across to get to one point to another. So 6I and 4j means we go 6 across and then 4 up. Okay, that it just tells me the direction to go. Okay, essentially. The displacement from B to C is then 5i minus 12j. Then it says for part A, what is the magnitude of the displacement from A to C, which is this vector here. Okay, now I don't know what A to C is. I don't have anything about A to C, but I can consider vectors because I know from A to C. Well, I can't go from A to C directly, I have no information, but I know if I go around the triangle from A to B and then B to C, I can also get to C that way. So then I can say from A to C, alternatively I can go from A to B and then B to C. Okay, and I know what these two vectors are, I'm given them. So AB is 6i and 4j, and then B to C is going to be 5i minus 12j. So what I can do here is essentially just collect like terms. So if I collect the i's, add the i's, 6i and 5i would be 11i, and then 4j take away 12j is minus 8j, and that is my vector. Okay. Now the magnitude is going to be, well, the magnitude, the sort of length of this vector then. So the magnitude, so AC here, the double bar, which means the magnitude. Again, that's going to be the root of the two parts all squared, so 11 squared and then minus 8 all squared. And that would be root 185. And there we are. And that would be in meters, okay? It's a length, it'll be in meters there, okay? And so think about what that's saying as well. If the displacement is this vector, then the distance is here. The distance, which is the magnitude of the displacement, okay? Which we went over. So that's the distance from A to C. Now, part B says, what is the total distance the man has walked in getting from A to C? Now, with that in mind, the total distance the man has walked from A to C would not be root 185, okay? Because in actuality, we're told up here that the man walks from A to B, then B to C. He did not walk from A to C directly. That's not what happened. He walked along this path here, along the triangle from A to B, then B to C. So it's not the distance from A to C directly. We need to work out the individual distances from A to B and B to C, because that's where he actually walked, right? So we know what AB is. Firstly, AB. AB is 6i and 4j. And so the length of that then, so the magnitude of AB is going to be root 6 squared and 4 squared, which would be 2 root 13. Okay. And then B to C, again B to C then is 5i minus 12j. And so therefore the length of that vector, length BC, the magnitude is root 5 squared, add minus 12 squared, which would be 13. Okay, so the total distance the man walked is actually, because he walked from A to B then B to C, it's these two added together. And so that would be, well, it doesn't simplify, but as a number, as a decimal, that's 20.2 meters to 1 decimal place. Okay, and so there we are. Okay, so we're going to look at some exercise questions to practice a bit further what we've done. So again, we've got some stuff to do with velocity and displacement here. So here we're told a man walks from his home along a straight road to a shop with speed 2.1 meters per second and walks home again at speed 1.8. Okay, so we're given a diagram here. Let's have a look. So this is home here. This is home. Again, I'm told that forwards is the positive direction. So in other words, walking towards the shop at the end here is positive. Now, we're told he walks home. He walks from his home to the shop with speed 2.1. We can say then that the speed is 2.1 meters per second. Okay, towards the home to the shop. And then we're told he walks home again at a speed of 1.8. So from the shop to the home, which is going to be that way now, is 1.8 meters per second. But but because it's the opposite direction to the positive direction, that means the velocity of this is going to be the negative. So it's going to be negative 1.8 meters per second if he's going from the shop to the home, because it's the opposite way. Then we're told he jogs along a straight road from his home to the park with speed 2.7. So from the home to the park would be that way. And we're told the speed is 2.7 there. Okay, from the home to the park, 2.7. But again, it's the opposite direction to positive. So that would mean it'd be a negative, that'd be a negative velocity. Okay. We are then told that he returns home from the park at speed of 2.5. So from the park to the home would be that way, 2.5 meters per second. And that'd be positive actually, because it's in the positive direction. It's going forwards instead of backwards. So we added on the speeds, or the velocities technically. So then it says, taking the positive direction, state the man's velocity on the journey from his home to the shop, which is going to be this velocity here, right, from the home to the shop. That's going to be 2.1 meters per second. Okay, part B, the displacement from his home when he reaches the shop. So from his home when he reaches the shop, so from the home to the shop, the displacement, well, the distance is 500 meters and it's in the positive direction. So he travelled 500 meters in the positive direction, so it's just 500 meters. Okay. Part C, the velocity on the journey from the shop to his home. Okay. So now we're going that way again from the shop to the home. Well, we just discussed it's minus 1.8 meters per second for the velocity there. Okay. Then part D, it wants the velocity from his home to the park. So from the home to the park, it's going to be that one. It's going to be that way. So minus 2.7 meters per second. Okay. And then part E, the displacement from his home when he reaches the park. So from the home to the park, well, it's 750 meters, but this 750 meters he walks is in the other direction. So it's not forwards, it's backwards, right? From the home to the park, it's backwards 750 meters. So it'd be negative 750 meters because he walks 750 meters, but in the negative direction. Then part F, we want the velocity on the journey from the park to his home. Well, as we discussed, from the park to the home is this velocity here. So 2.5 meters per second. And there we are. So again, that's the idea of displacement and velocity. So there's sort of the speed and the distance, but in the positive direction. Okay. If it's in the opposite way, then we have to make it negative. Okay. Cool. Okay, we've got this question here. We've got this final question here. So we're told here a plane flies from P to Q and then from Q to R. Okay. Again, we're given the two vectors, the two displacements from P to Q and then Q to R here. Then it says for part A, find the magnitude of the displacement from P to R. So the displacement, or sort of the vector from P to R is here, right? This here, but we don't know what that is. We're not given anything about P to R directly. We don't know anything, but what we do know is we can go across the triangle. We can go from P to Q, then Q to R. So from P to R, we could say it's P to Q and then Q to R, right? And we know what these two vectors are. PQ is 100i at 80j, and then QR is 50i minus 30j. So if we just add these two vectors, well, 100i, 50i is 150i, and then 80j minus 30j is 50j. And there we are. So then the magnitude is the magnitude of this vector from P to R. And so that's going to be the magnitude of, so the root of the two parts all squared. So 150 squared and 50 squared. And that would be 50 root 10. And it's in meters. Okay, and so there we are. And so again, so this represents the distance from P to R. Okay, this length here. Okay, cool. Then part B says to find the total distance the plane has travelled in getting from P to R. Okay, so the distance the plane has travelled, again, the plane actually travelled not from P to R directly. It did not travel along that route, but he actually went from P to Q and then from Q to R. So actually, where the plane actually travels is along these two routes here. So we need to find the length of these two routes. So firstly, PQ, where PQ is 100i, add 80j. Yep, so the length of that, so the magnitude of PQ is going to be root 100 squared add 80 squared, which would be 20 root 41 meters. And then Q to R here is 50i minus 30j. And so the length of that is going to be, the magnitude will be root 50 squared add minus 30 all squared, and that would be 10 root 34 meters. And there we are. So therefore the length he travelled, distance to plane travelled, again, he travelled along P to Q, then Q to R. So we add these two lengths. 20 root 41, add 10 root 34. So that is 186.4 meters to one decimal place. And there we are. Okay, and then part C says find the angle of the vector PQ. Actually, the textbook's wrong there, because I looked at the answers after I did PQ to find that they meant PR, P to R. So the vector PR makes with the unit vector J, okay, not PQ, okay. So P to R is what they're after. Textbook has silly mistakes, but yeah, anyway, we have PR, which is obviously the vector here. We found PR in part A. So PR is 150i and 50j, okay. So if I remind you then, PR is 150i and 50j. So it's talking about what the angle it makes with the vector j. Now again, it's talking about angles. It's best to sort of plot the vector, right? Plot the vector, sort of plot the point, right? To visualize the angle. So again, if we draw a sort of coordinate grid, so firstly 150i, that's going to be 150, say, on the axis here, and then 50j will be positive 50, say, here. So then if we plot the point there, that's my vector. That's my vector there, okay. Now it's talking, so 150 there. Now it's talking about the angle the vector makes with j, the vector j. Now as we discussed earlier, again, there's this sort of x-y axis of vectors, I and j. I is sort of the x-axis and j is basically the y-axis, okay. So if it's talking about the angle it makes with the vector j, basically it means the vector it makes with sort of the y-axis. So this angle here, from sort of the y-axis to the vector line there. So if we sort of construct a little triangle then that it makes, if we, there we are. Well, firstly it goes 50 up, okay? So 50 upwards, and then it goes across by 150, okay? Okay, so we get this triangle here. Okay, so we've got this angle theta, and so we go 50 up and then 150 across. Hopefully you can see that. Okay, and so then at this point we can use a bit of SOHCAHTOA to find the triangle. Again, theta is opposite 150, so opposite here, and then the adjacent is 50. So if we use SOHCAHTOA to find theta, so tan theta is opposite over adjacent, which is 150 over 50, which goes to 3. So therefore, if we do inverse tan of 3, that would be theta. So theta would be this. So if we do tan inverse of 3, we get 71.57 degrees to 2 decimal places. Okay, and so there we are. That's it. I'll see you next time.